Okay, let's talk about the engineering design process. Now, what is typically called the engineering design process is really just the process of how you would engineer anything. It's all about how you, as an engineer, should approach a complex project. So let's get started. ABET defines the engineering design process as this gigantic paragraph of stuff right here. Now remember what ABET is. It's the Accreditation Board for Engineering and Technology. It is the group that accredits engineering departments at universities and colleges. So that's what ABET is. So here is the ABET definition of the engineering design process, and let's just read through it. Engineering design is a process of devising a system, component, or process to meet desired needs and specifications within constraints. All right, that says the whole thing right there. First of all, it is a process to design things, and you have to have specifications, and it has to be within certain constraints. Now, those constraints can mean a lot of different things, so let's read on. It is an iterative, creative, decision-making process in which the basic sciences, mathematics, and engineering sciences are applied to convert resources into solutions. Engineering design involves identifying opportunities, developing requirements, performing analysis and synthesis, generating multiple solutions, evaluating solutions against requirements, considering risks, and making trade-offs for the purpose of obtaining a high-quality solution under the given circumstances. For illustrative purposes only, examples of possible constraints include accessibility, aesthetics, codes, constructability, cost, ergonometrics, extensibility, functionality, interoperability, legal considerations, maintainability, manufacturability, marketability, policies, regulations, schedules, standards, sustainability, and usability, and a whole bunch of words were just there to describe what should be a pretty simple idea in that engineers make stuff. That's it. That's what engineers do. Engineers make stuff. So that's ABET's definition. Let's go on and look at some others. Here is the NASA engineering design process. Now, they don't specifically lay this out anywhere, but they do utilize this. First of all, you identify the problem, whatever that happens to be. You identify criteria and constraints. You brainstorm possible solutions. You select a design. You build a prototype. You test and evaluate that. You refine the design, and then you share the design. So that's the engineering design process. It sounds a lot simpler, a lot less words, but essentially the same process that ABET described there. Here's the American Society of Mechanical Engineers, the ASME, and here's what they say. The engineering design process is divided up into these 6 steps. First of all, problem identification, conceptual design, preliminary design, detailed design, prototyping and testing, and final design and production. Now, this is a lot more familiar to me because this is the general process that I used when I was an engineer to come up with final solutions. Now remember, I was a software engineer, not hardware, so I'm not mechanical engineers, but nevertheless, the same general process applies no matter the type of engineering you're in. So what kind of common elements would we see? Well, I've taken several different engineering design processes. Remember, there's no standard for what is considered the engineering design process. And I have identified similarities between those, and I've kind of put those together into these 7 steps. First of all, you got to know what you're working on. That's the problem identification. So you want to identify the problem, you want to understand the problem. Now, in order to understand the problem, you need to do some research, and you probably need to start brainstorming some solutions. So number 1 and number 2 are kind of the same thing. Number 2 is a little more into the problem where you can start imagining solutions. Now, brainstorming is not usually something that you do by yourself. It is something that you do as a team, usually. And the idea of brainstorming is that there are no wrong ideas. You don't want to discourage anybody who is coming up with wild solutions for the problem, because sometimes those wild solutions will spark somebody else into thinking, hey, a part of that idea could be used here. So brainstorming is just wild speculation, and you want to encourage that, especially early on in the design process. So research, brainstorming is step number 2. And then you back off and you start saying, okay, well, yeah, we need to narrow this down now. Let's analyze some of the solutions that we came up with and see which ones are the best. We would need to optimize those solutions so that we can maybe test them out. And that's step 4. You start prototyping and you start testing your solutions. Okay, now this whole thing is an iterative process. So step number 5, you start refining things, and maybe you realize, hey, we need to go back and change our original design because we ran into a problem. That's the process. It's an iterative process. So step number 5 is iterative refinement. Finally, you end up with some kind of solution, so you have to implement it. You have to put all the pieces together. The solution may have required development of hardware and software so that those two things could be developed in parallel. You don't just develop the hardware and then the software, you do both of those things together. So at some point, all of the pieces have to come back together into some final implementation. And then step number 7 is this, and it's more a statement than it is a step, because every one of these steps needs to be documented. Even the brainstorming needs to be documented. And there's lots of documentation in the engineering process. I'll show you a little bit more about that. We've kind of touched on that in previous lessons here, but we'll talk even more about it this time. Here is a block diagram that shows somebody's idea of what the engineering design process should involve. You can see, starting up here at the top, define the overall objectives, gather information, this is research, identify and evaluate possible design strategies, this is analysis, choose / change the design approach, and then make cut at the design. Then you model, you analyze, you build. Notice documentation is there. So you build, document, and test. Even the tests need to be documented. Does it still meet the specifications? If yes, you can continue on and finish up. But if no, which is most likely if you're the first time through this process, then you need to say, well, is this approach still promising? If it's not, then you go back and you choose or change the design approach. And this inner loop here, this inner loop here, where you revise things and then model, test, retest, ask yourself, does it still meet the specifications? That is the most time-consuming portion of the whole entire process, usually. This is the actual doing here in this inner loop. At some point, you end up with a design that meets all of the specifications and you think it's just right. So you move on to test the final product. This is where the hardware and the software come back together. Okay, then does it work? Yes? All right, then you're ready to move on. If no, well, again, iterative process, you need to start all over. All right? This slide here is actually a slide from my old work. This is a software development, distinctive phases of software development for projects. Now, one of the things that I did as an engineer is I helped teach other upcoming engineers. We would have new hire classes where all of the new hires would come together and we would sort of teach them the process. And one of the things that we taught them was this waterfall diagram. What's called a waterfall diagram starts up here at the top and it goes down. So you can imagine water falling down each of those steps there. But here we start with the customer mission requirements. So this is requirements that come from the customer. Now the blocks that are white here are typically blocks that involve somebody who understands the big picture here. We would call that a systems engineer. This is someone who understands the project at a higher level than anybody who is like going to write some code or who is going to build a black box. So the systems engineer are white blocks. The blue boxes here would be like people like me that were lead engineers, and then you'll notice they turn white down here at the bottom. That's because the systems engineers need to come back into for what's called the integration phase and the verification phase. But let's go through this. First of all, a customer talks to a systems engineer, and systems engineers create what are called system requirements. So this is the defining of the problem here. Now, once the systems engineers have done their job, then somebody comes along and divides this up into hardware. You'll notice this is the hardware branch, and then down here is the software branch. Well, since I was the software person, this software area is much more detailed for my purposes. And this hardware area would have its own set of steps the way that the software does. But that's hidden to me because I didn't really care about that as a software engineer. So the hardware requirements come here, and you see there's hardware design, fabrication, and integration cycle. Okay, there's a lot of details left out in that one block, but you'll notice it comes back together down here after all of these software steps have been done in the integration phase. So this is where you start integrating the hardware and the software back together. You do some preliminary verification, and then finally a formal verification. But after you have the system requirements and the software requirements divided out, then the engineers get those software requirements and they start designing things. And one of the first things they do is they come up with what's called a top-level design. So they kind of break things up into tasks or into modules, and they start saying, okay, well, this needs to happen over here on the left, this needs to happen over here on the right, down the center we need to do this. And then you start breaking things up into module, and then you come up with a more detailed design for each of those modules. Okay, you can think of those modules as like tasks. So here's the detailed design. So it's a top-level design and then a detailed design. And all of that happens, everything from this module upward happens before you sit down at a computer and start writing code. Because then this little module right here, this little rectangle right here, is where you code and test the modules. So this one takes up a lot of time because this is where groups of engineers get together and they write code. But nevertheless, this is the most, this is the project right here. This is you creating right here. But all of this other stuff is part of the engineering process. And every one of those steps requires documentation. Finally, integration is where the hardware and the software come back together. And like I said, preliminary verification and formal verification. Now, this is just stressing what I've already said. First of all, documentation is important. I hope you understand that now. And every step of the process must be documented. And a good question would be, why? Why does every step have to be documented? And here's the answer. First of all, you may not be around to work on this project the next time it needs updating, or the next time that someone does a similar project. So you need to write all of the documentation down for future posterity. That means for people that come along that don't understand what you did, they need to be able to peek inside your mind in order to figure it out. And that's what documentation is. It is a peek inside your mind to figure things out. Okay, so why do we need that? For future posterity, so that people can peek into your mind and see what you were thinking and the processes that you went through in order to develop this final project. But you also need it for lawsuits, because anytime there is a lawsuit, the other side can do what they call discovery, and they can go and they can take all of your notes. That's why those notes are important. They're not just important for you, they're also important for all sides in a lawsuit, because they can either condemn you, or if you're being an honest, legitimate, good engineer with lots of documentation, they will protect you. Not you so much personally, but you meaning the corporation, the company that you work for, the engineering firm. So lawsuits are just a fact of the engineering world. And the sooner you realize that, the better you'll be. Typically, it's not the junior engineers that have to worry about that. Typically, it's the licensed professional engineers and the firm that needs to take care of that. So they're going to, along the way, make sure that you are documenting things all along the way, every step of the process. So documentation is important. All right, here is a more detailed look at that same figure, that same waterfall diagram that we just had. First of all, customer requirements, system requirements, divided up into hardware and software. And you notice the hardware branch just continues on until we get back to system integration down here, and then you have the verification process. Okay, but let's follow through the software requirements. First of all, the software requirements have documentation associated with them. Each one of these numbers that's over here to the side, to the right-hand side of each one of these modules, is documentation. It represents documentation. So a 922 was a document that had software requirements in it. Then the 923 was the document that described the top-level design. And then the 926s, and you notice there's a stack of them here, so there's lots of 926 documents. Those are the detailed module designs. Now that could be comments that are in the software itself, but it could also be external documentation that exists outside of the comments. In fact, in my branch of work, oftentimes the software engineers would write huge comment blocks at the beginning of a program, and then that block was taken out and put into external documentation. So it was sort of like, here's what this module does in some detail. Okay, then here's the code and test phase. That's a 914. That's just a testing document. And then down here, these other blocks here, each one of these requires some documentation as well. First of all, after the top level design, you need to start putting things into what are called demonstration milestone plans. So a DM plan. A DM stands for demonstration milestone. And it's typically after you do a demonstration milestone that the customer comes along and starts paying you. So it's not the finished project. Let's say you have a multi-million-dollar project that you're working on. Well, it might be broken up into 12 different milestones. Say you're going to complete it. You're going to complete this multi-million-dollar project in 12 months. Well, you need to have a DM every month, let's say. Well, after you do the first DM, the first demonstration milestone, you're demonstrating to the customer that you are making some progress on the project. And at that point, the customer, according to the contract, may write a check out to the corporation that may be 1/12 of the entire project, because you're dividing it up into 12 DMs. So DMs are where the engineers demonstrate that progress is being made toward the final project, and the customer agrees and will write you a check for a portion of the contract. And then here's development milestones. There's the DM plan, and then there are the actual DMs, the actual development milestone. I said demonstration milestone, development milestone is the same thing. Okay, system design integration plan, that's another document. See, it says 933 down there. That's another document. And then that integration plan has to go into the systems integration. So once again, remember what this is. This is where the hardware and the software come together. And then we begin the verification process. Okay, but notice there's other documents down here, the user's manual. Somebody needs to write a user's manual. Now, oftentimes you can't write a user's manual until a lot of this work is already done, because sometimes you don't know how to use it. There may be things that the user has to do that you didn't see right at the beginning. So the user's manual needs to be part of the process. And then here is the ATP, otherwise known as the acceptance test procedure, and all of those things go into the formal verification process. Okay, so the customer comes back in and looks at things and makes sure that, hey, this is exactly what I wanted. Now, if you have kept the customer up to date throughout this entire waterfall process here by giving them good, strong demonstrations and development milestones so that they are aware of what's going on and what's changed and what hasn't changed, then the formal verification is just a matter of checking a box and demonstrating the final product, because the customer should be aware of what's going on. If you kept the customer out of the loop and just brought them back in at the very end, they may say, hey, that is not at all what I wanted back here in my requirements. Why are you guys trying to sell me this piece of crap? But if you keep them involved in the development milestones all along the way, then they understand what has changed and what hasn't changed in the process. Remember, it's an iterative process. That means things change all along the way. Be sure you keep the customer in the loop. In my circuits class, I have students do an engineering project as sort of a capstone for the class. The circuits class is oftentimes the last class that many students take while they're here. This is an example of a past project that I had my students do. You may know a CNC as a device that can cut out shapes in either wood or metal, but this was going to be a plotter. So it was a CNC device using CNC technology that's pretty well established these days. I wanted them to draw a picture, okay, and that was it. So the CNC was not a cutter or a router or anything. It was a pen. All right, so they needed that to draw. Now this was in spring of 2019, so this is pre-COVID. And what this binder right here, this is like a 4-inch binder. What this binder includes here is all of the documentation for the entire project. The first page is a letter to the next leader. Then they were required to do some safety training. So this is health and safety agreements. Every member of the group was required to view certain videos that were to be training, and then to sign off on the fact that they had been trained. Here is the 922. I use the same numbering that I'm used to from my work, so this is the project requirements. Now the students had to make their own requirements document in conjunction with the customer, and I would be the customer. So here they are. There's a picture of their device, and then here the document had to be signed off on by both myself and the lead engineer, and then the table of contents, and then here's the intro. The goal of this project is to design and build a fully functioning CNC plotter. This task will be carried out by the engineering lead, led by Miguel Gutierrez, and the CNC plotter shall satisfy the specifications of the customer, which are agreed upon by the engineering team and the customer. The project is a fulfillment of course requirements for Electric Circuits 1 at Tyler Junior College for the spring semester of 2019. The key goal of this project is to ensure that the CNC plotter can take inputted images from a USB drive and trace out detailed images. The CNC plotter should be able to trace out images up to a maximum of 11 by 17 inches on paper, and all standard paper sizes beneath those inches. Okay, here are the requirements though. Now let's look through this. There's the project requirements. Here's the additional requirements. And then here are some concerns, safety concerns, mitigations for the safety concerns. Here's a project schedule. Here's a schedule concerns, mitigations for the schedule concerns, project costs, so they did have a budget, and then additional information, and then appendices. So let's look at these requirements here just a little bit. First of all, you'll see that there's a heading here, 2.2 point project requirements, and then 2.1 is a size requirement, 2.2 is operation requirement, 2.3 is access requirements. So every little thing needs to be talked about in terms of the requirements. On the size requirements, 2.1.1, the CNC plotter shall be a tabletop model of no specific material requirements. 2.1.2, the CNC plotter shall be capable of drawing on paper of dimensions up to 11 by 17 inches and any standard paper size below this. Operation requirements. The CNC plotter shall be able to operate from a flat horizontal bed. The CNC plotter operating bed shall have a simple and functional paper securing mechanism. All of those little details. Let's see, here's axis requirement. It needs to be able to move in X, Y, and Z. The Z is just to pick up the pen. The writing tools, it needs to be something like a Sharpie that you can buy off the shelf. Motor control requirements, it says the CNC plotter shall use an Arduino Uno microcontroller development board, and the Arduino Uno microcontroller development board will be provided by the customer. So that was me. And the main board requirements, we're going to use a Raspberry Pi, so forth. Image input, you can use a USB 2.0 or 3.0 memory stick. The motor requirements, something about the motor. Graphical user, here's power requirements, operated off of 110 volt AC. And you're going to have to convert the AC into DC for the motors, because the motors are DC motors. Additional requirements include things like, here's the documents. You need to do a 922, a 923, a 926. That's the requirements document, the top level design document, the detailed design document, and then the deadline for the demonstration plan document is set. And everything has deadlines on it as well. And then here's project demonstration requirements. Development milestone 1, development milestone 2. They had to participate in the Makers Fair project, so we considered that a development milestone as well. And then final project milestone was at the end of the semester. They also had to produce a group video of the process that could be uploaded to YouTube. And they needed to give me timesheets each week and status reports. And students were graded on the amount of time that they devoted to the project and the status reports. And because I was the customer, this was the way that the customer was involved, so that there were no surprises at the end of the semester with, hey, student X over here decided they don't want to participate anymore. So it would not be a surprise to me if they kept me updated in the status reports. Okay, and then safety concerns. Here's the mitigation for the safety concerns. Project schedule. You can see it's got some dates on there. Here are the schedule concerns, and then here's the way to mitigate the schedule concerns. There probably should be a space between those two things, but there's not. And then here's project costs. They had a budget of $300. And the way it works is they buy the stuff, and then I have to reimburse them at the end of the semester. Okay, and then here is ownership. At the end of it all, it belongs to TJC. Okay, and then here's the 923. Here's the 926. That's the detailed design. Let's see, what else have we got? Here's the user instruction manual, and then that has lots of sections, and you can see there's quite a bit here. Here's development milestones, demonstration plans, and the customer needs to sign off on all of those as well. And then here's the group status reports and so forth. So you get the idea. Okay. This is what I use for my class, and you can see it follows the engineering design process that we talked about. All right, let's move on and talk about your assignment for this week. All right, your assignment for this week is to go take the quiz over the engineering design process, and just like always, you get multiple attempts at that, but it's a limited number of attempts, so be aware of that. And then I want you to take a project that you've already done, like your bridge project. So use your bridge project that you're doing in lab, and it doesn't matter if you do the drawbridge or the popsicle bridge, either one of those, and write a requirements document. So imagine that you're a bridge expert and some customer comes along and says, hey, I need a popsicle bridge that can bear such and such weight and can span such and such distance. And I want you to write the requirements for that as if it were a real project, just like you saw in the requirements document that I just showed you. So make a short, it doesn't have to be a whole document, don't want it to be a whole document. I just want the project requirements portion. So tell me what should be the requirements. So number 1, number 2, number 3, and so forth. So just to get you in the process of thinking about projects here, I want you to make a requirements document. Okay, that's it. Let me know if you have any questions during the week, and hopefully you have a great week.